think you can, yeah. So I think you can, I will in this talk mainly talk about the observational perspective, which actually people are doing in the 21 centimeter cosmology. So I will talk about the visibility based power spectrum estimation. And this talk mainly based on these two paper in the archive, it is in the archive. Uh, so a bit of introduction, what we want actually at the end of the day is to map the universe, basically the 21 centimeter signal, and from observed data, basically the UV data visibility, and we want to make an image of the universe, 3D image of the universe, that is the cube, But the problem is that in our actual observation, noise is much higher as compared to the 21 centimeter signal, which is very faint. And we will get as a noise at the, so this is the motivation for going to the higher the statistics, that is the power spectrum. In the image plane, which person discussed now, you can make a image other radio sources like the galaxies, supernova, all these things you can make images, and you can see the features, large scale structure. But in 21 centimeter cosmology, still the current observational techniques or the current observational data are not going to give us a image like that. So the noise is much higher. So we have to go some other techniques which we can do now. That's why that is the motivation for the going to the power spectrum, basically the 2-point statistics. So we are going not to the, in the 21 centimeter signal, we are not going to make an image of the signal. Rather, we are trying to detect the signal statistically in terms of the power spectrum. I will explain what is the power spectrum now. Power spectrum, what is that? You have the image in the 3D cube. What you can do, you can just do the Fourier transform, basically make an image, make 3D FFT, and you now your observation are in a Fourier plane. Now amplitude of this Fourier mode will give the power spectrum, that is called the power spectrum, and that is interesting. What is the advantage? That the signal to noise ratio is much higher as compared to the image domain. So that's why we are going to the power spectrum plane, power spectrum level, not to the image. Now we have to correlate somehow. So our interstate quantity is the power spectrum, and you had a lot of talk about the visibility, basically the 2-point visibility in the UV plane or in the Fourier domain. So you have to correlate these two quantity, which we want and which we have. That two quantity we have to correlate. So I will not go to the 3-dimensional power spectrum for the now that I showed. I will go only to the 2-dimensional, basically the angular power spectrum. We are measuring the fluctuations only in the 2-dimensional sky plane. So the power spectrum mainly give you the fluctuations in the 2D plane. Just a basic, just a recap, what we are measuring in the radio interferometry is a visibility. What is this? It is the electric signal correlation of the two antenna. If you have many antennas, you will get many visibilities, and this is called the visibility. Actually in physical, what it is the Fourier transform of the intensity of the sky signal, but it has some sky response, antenna response function, that is called the primary beam. So that left hand side, what you will get in an interferometer, and this is the Fourier transform of the sky signal, but multiplied with the antenna response, that is called the primary beam. This, so we can decompose this observed visibility in two terms. One is the signal term, which is only due to the sky signal, but all the instrument, all the electronics is come up with some noise. So that is some instrumental factor is added in the right hand side. So visibility we will get with some noise function. And as I have said, this I will talk about the angular power spectrum. What is basically the not we are not considering in this talk the three-dimensional structure, but only the two-dimensional structure, that two-dimensional fluctuations. And same, you can do the 2D Fourier transform. You will measure the power spectrum. Now we know what we want. We want the two-dimensional amplitude of the Fourier mode. And what we have the visibility, which is the Fourier transform of the sky signal with some instrumental noise. Now we have to correlate these two terms. How are they related? So that we can say something about the sky signal. Let's go to the again. This is the one model of the primary beam that I have talked about, the primary beam. And this is the sky signal. And what you will get from the sky signal, that is the same Fourier transform multiplied with this primary beam. But we can write this as a Fourier, means the convolution. You can say that the primary beam is multiplied with the temperature fluctuation or intensity fluctuation in the right panel. In the left panel is the primary beam, and this is multiplied, and the visibility is the Fourier transform. So from the Fourier transform relation, you can write it as the convolution. What is that? Convolution of the Fourier transform of the primary beam and Fourier transform of the temperature fluctuations. Now our observed quantity, that is only the signal part in the left hand side, is the convolution of the temperature fluctuation, or basically the Fourier transform of the temperature fluctuations, but with a convolution of the primary beam, that is the instrumental response. So now you get some relation of the temperature fluctuation that we want to measure, delta T tilde unit, and left hand side the observed quantity. Now again, but this is Fourier transform, and power spectrum, what is it? Is 2-point correlation. Why you are doing this? Just to make the signal to noise ratio much higher, so that the noise is less. So that's why we are going to the 2-point correlation function, the power spectrum. What we have to do, we have to correlate this visibility with another visibility which is separate. The U is the measuring at a certain Fourier mode or certain antenna separation. If we go to this plane, so these two antennas are separated by distance d, and if you're observing wavelength is lambda, d by lambda, basically the unitless quantity, that is called the baseline. So in the visibility, generally we use this baseline parameter u as a basically the parameter as a visible. We measure the visibility as a function of the baseline. Now what we are doing? We are doing the correlation of the visibility at a certain baseline with another baseline that is we separated. Why we are doing this? Because you can do simply, but because this, when we are interested in the amplitude, we can just come multiply with another. This is visibility of the complex quantity. Now if we multiply with complex conjugate, you will get the amplitude square. But we are doing at another baseline, means that we want to avoid the noise. I will explain that why we are correlating with another baseline. So this, what we are doing here, we are correlating the visibility at certain baseline to another baseline which is slightly separated. What it will give? It will give, so now I am writing only the signal part. As I have said, this visibility is sum of the two components. One is the sky signal, which is the Fourier transform of the sky signal with some primary beam, and another is the noise. Now what the signal part will give? This is the, as I said, this is the convolution of the primary beam, the Fourier transform of the temperature fly sky signal with the primary beam. So this A tilde is the Fourier transform of the primary beam. Now if we correlate visibility with another, the primary beam will also be there, because this is with a convolution. and it will give another term that is called the power spectrum. So this delta T and delta TU prime will give you the power spectrum, and this, when you are correlating with another baseline, this primary beam convolution will be there. So that I am writing here, the convolution of the visibility of the sky signal with another baseline. So this right hand side has some relation of the measured quantity and the interested quantity. This power spectrum we are interested in, and the left hand side is the measured quantity, because you can measure the sky signal, you can correlate, you have many visibilities at different points, and you can correlate them. This left hand side is the measured quantity, and this power spectrum is the we are interested, but still the convolution is there. So you have to somehow normalize these things to get the actual quantity, because you have to say something unique, because this is a parameter, the primary beam are the antenna dependent. If you change the antenna, this factor will change. So we have to say a quantity which is due to the sky signal and which is normalized. So this you have to normalize these things. Now, so again, I am writing the here. Now I am introducing the noise part also. So here the noise comes. The right hand side have another term, sky signal, I have explained, and the noise term will give you a Dirac delta function when you correlate, because the noise is correlated only at the same baseline, because the instrumental noise is independent at different measurements. So now suppose you measure now the visibility at now at 5 times at so 1 hour later, this noise will be totally uncorrelated. Now you take, when you take the ensemble average of this quantity, it will be goes down. But you will, when you correlate the same visibility, same noise, it has some non-zero part. So that is the technique we are using. We are not correlating the visibility with same visibility, because the noise will give you, we don't want noise. Somehow we have to remove noise. So that's why that is the one technique. We are correlating the visibility with another visibility to remove the noise, and this signal will be correlated because the sky is not changing too much. So sky will be the same, and this sky signal, this correlation will give you the signal part. Now we are now the uh, relation between this observed quantity and the power spectrum is defined here. This CL I am writing not P as a power spectrum, because we are doing in a 2D Fourier transform, basically the angular power spectrum. So that is denoted by the C. The idea is that you have, just to summarize all of these things, what I have, yes, yes, please. Okay, so just to summarize these things, we want power spectrum. Why? Because imaging is not possible in the 21 centimeter studies, because noise is much higher. That's why we go to the power spectrum. But sky signal power spectrum is not exactly the you will give, what you will get directly from the interferometer. You have to somehow correlate this quantity. So what we are doing, we are doing the visibility correlation, 2-point visibility, one visibility here, we take another visibility, another point, we are correlating to avoid the noise, and finally we will get the power spectrum with some normalization, that is V0. And this theta 0 I will explain. Basically this theta 0 is the primary. If you correlate, if you do the actual calculation, actually the calculation is there in the reference. If you do the actual calculation with a Gaussian beam with some theta 0 width of the primary beam, because you know, when you observing sky with some telescope, you know what is the primary beam width and what is the theta 0 values, and you can normalize these things easily, and finally you will get the angular power spectrum. So that is the relation. Again, Another thing we have to consider, this correlation, the sky signal is not correlated up to the whole UV plane. So that is what I am plotting here. I fixed one visibility at U, and we change all the visibility at delta U. I changing that. Let's see how much this signal we can correlate to increase the signal to noise ratio. So in that plot, what I am showing, this U is fixed. I am changing the delta U here. So this plotting, this is one simulation plot, and you can see that after 25, but this is again antenna dependent and the frequency dependent, primary beam dependent and the frequency dependent. For this study, if you see, if you correlate, suppose up to 40 baseline, you will get the zero correlation because the signal falls. So you have to restrict your correlation region. So, okay, I will correlate only that much, suppose 20, so that our signal is correlated, noise is different. Again, this is due to the noise cancellation. We are doing the visibility correlation at two different baselines, and we can go up to some point. We can't go the whole UV plane to correlate. So you have to go some UV distance, and you can correlate all the visibilities to make your signal to noise ratio much higher, and finally you will get the power spectrum. So that is the whole visibility calculation of the theoretical development of the power spectrum estimation from the two visibility correlation. Yes, do you have any questions now? Okay, so now this two visibility correlation formalism, we have developed some estimator, because you can simply do the two visibility correlation of them. Thus, there are lots of other complications also, so that your measurement is quite accurate. Also, the signal to noise ratio much higher, because your signal is very faint in your 21 centimeter cosmology. So that's why you have to develop a efficient estimator, and also it takes huge time, because when you are correlating, suppose 7 lakhs 8 lakhs visibilities per observation per night, your computation time will go off. So you have to consider all of these things, and we have developed an efficient estimator to estimate the power spectrum from the visibility. So this is one of the example plot of the UV track. Suppose this each point is one visibility here, and this track are due to the earth rotation. So each antenna pair will give you one visibility measurement. Now if you observe the sky for the whole night, you will see like a track of these things, and you can correlate all of the visibilities up to some distance that I told, suppose 25 in the earlier plot. So you can correlate all the visibility around this point, suppose this here center, and you can correlate all the visibilities within with the circle of 25. Yeah, and you can get a power spectrum measurement. So that is one of the UV track, and we are correlating all the visibilities and with some distance, and finally we will get one power spectrum. So that is I'm showing uh, uh, in one plot here. This is a symmetric diagram what we are doing. So this is same, basically the UV center here, and this is one of the baseline point here, suppose this one. Now this circle here we are correlating, as I said, this the signal will contribute, the signal correlation will be non-zero up to certain distance, but if your distance is much larger, your signal correlation will zero. So you can't correlate this point and this point, because you will get zero correlation. So this circle will give us a signal correlation, and you can take all the pairs in this circle, and finally you will get one power spectrum for that beam. Again, you can take another circle, you will get another measurement here, you will get another measurement, and these all points will give you one power spectrum. Basically this is called the binning. Why we are doing? Just to make the signal to noise ratio much higher. You are measuring the same sky signal, signal is isotropic, so you are taking all the measurements here and taking the average to signal to make the SNR much higher. So that is doing, we are doing here, that is Bayer estimator. We are correlating all the visibilities vi vj. Ij is the, so suppose I and j over this j is all the circle, again you change I, it will be correlation of the j. So that is we are doing. And the denominator is the normalization constant, basically that I talked about, the v0 quantity that is depend on the primary beam width. So finally, when you do all of these calculations in that visibility UV track, so suppose I am here and I take this circle and this annulus region, and we do all the measurement, and finally we will get one power spectrum estimate for that beam. Next, I can go to the another beam, you will get another power spectrum. Another beam in the lower baseline range, you will get another power spectrum. So, and this weight factor wij I am taking as a delta function, because we don't want the self correlation, it will give the noise bias. So we have to avoid this somehow. So delta I is 1, basically the weight will be 0 when it is same. When it is not same, it will give some non-zero value. So we are not correlating the self correlation. So based on this formalism, we have developed an estimator, that is Bayer estimator, and it is developed, and also it is applying the GMRT data, and you can download this from this GitHub, and I can show you some of the demo here. Let me go to the terminal. Sorry. You can't see my screen, no? Okay, let me. Yeah. Can you see my screen, terminal?
Yes, yes, yes.
Okay, so I am just
terminal. That words are very small.
okay. How can I do that? It is okay.
Yeah, now it's too big. Yeah.
Okay. So, just I am copy paste uh, the command actually. So it is available in the GitHub, and you can download that, basically the two visibility correlation, and you will get a folder here, directory, that is called the Bayer estimator, and all the source file is here. What you have to do, uh okay, let me go to the mm, link first. Hmm. Yeah, so this is the estimator, and it is uses and output files, all the you can see some of the uh, input files, how it looks like, all the things are there, you can download and all these things, but I will show some of the results here, but you can check all of these. What you have to do, you have to make clean, but there might be some dependency issues. Please let me know if you have any difficulties in the installation, because these packages are depend on other packages, that is called the NRCP, and these all the things, their dependencies are there. Please let me know if you have any questions. So make clean, what you have to do. So there are some make file, you have to change your path, basically uh, where the libraries are there, basically the cfits io is written, because all the visibility files uh, are written in the cfits file. So your cfits io is the c library to read and write the fits file, and also other packages. I think we don't need all of this, but yeah, please check and let me know if you have any problem in the installation. So, and you have to just change the path here, at which path you have these libraries and include. So you have to change here. This is for my library located here, but you can check. Next, you have to make your yeah. So what you will get a executable file, that is the correlation v2. This is simulation, but yeah, this is for the data also. And you can, if you run that, so now your executable file is there, and you have to run this with your parameters or with your visibility files. So if you just run that, you will give you what you have to pass. So this correlate is the executable. Now you have to run the uv input fits file, that is the feasibility fits file. It assumes that your fits file is already calibrated, which Tosun and all knob and all the tutorial session you have done. It assumes that you have done all these processes: RFI flagging, calibration, if any point sources, if you want to, which source you are interested in, depending on your research problem, you have to fix your data. Okay, I am happy with this type of calibration or this type of flagging. Then you can pass this fits file after all of this, and what it will give, a output file that is called the power spectrum. And this you have to pass another input file. What is that? The input file, I have there some parameters you have to pass. Suppose your observed file is observed data file is certain channels. It is not only one single channel. Suppose 128 channels are there. Now this is channel one. You can change it any. Okay, I am interested in 10 channel to 20 channel. You can just pass that. Next is the, okay, how many baselines we are interested, because if you are interested in the diffuse radiation, it will reside only at the short baseline. So I want interested on the diffuse radiation, so that's why I restrict here 1,000. There are some low you mean also, because there are some limit in the, because you can't go to the zero, so there are some limits also. And this is theta 0, that is the width of the primary beam, and this is the another number, but because this calculation you have to do depending on your observation. So here 16 I have used, because the uh, circle of this correlation is 16 for our case, so that's why I put it there. But there are some other parameters which you can ignore now. These are for the variance calculation, and this is for the flag LL. If you have observed the data for RRL and L, both polarization, then you have to pass it 1. If you have only single polarization, that you can pass 0. So these are the parameters you have to give, and then you have to run this correlation v2 shim, then input fits file, suppose test.fits, then some piece power spectrum pspec dot dat out file, and this input file. I will not run that, but this is the format you have to run. And then what it will give, it will give you the power spectrum in this format. What it will give, it will give the u, basically the this one, u is this one, this center of that. And then you will give the power spectrum real part, and imaginary part you can ignore, and this is O8 also you can ignore. So this two column is interested here. U basically the center and the power spectrum of that beam. So this is the final output. Now I will show some of the result here. What is the result that we already got? This one. So this is one of the model power spectrum we have to, because we have to validate that, yeah, this power spectrum estimator is working fine. So that's why we know we put a simple power law power spectrum in our data, simulated data. Next, we apply the estimator in the input mode simulated data, and finally we got this with some error bar. So this validate our estimator is working fine. Now we can apply the in the real data also. Yeah. So any questions? Okay. Next is that there are some problems in that earlier estimator we have developed, because it takes huge computation time. So that I said, suppose your visibility is one night observation, 8 lakhs, 10 lakhs. If you do the multiple nights, then your estimator will fail, because it will take huge time to because the computational time goes at n square. Each visibility correlating all the nearest, then again go to the next. So basically it is computation is n squared time. So it takes huge computation time. Another problem is that wide field, because I will talk about that. What is wide field foreground and noise bias we have restricted. So these are the some problems in our earlier estimator that I showed. But it is okay for your if the signal is much higher. Suppose you are observing a galaxy in your local universe, your signal is much higher compared to the other foregrounds, and you are observing for a small time interval, suppose 5 hours, then it is okay. But if the problem for the 21 centimeter, that is not efficient, because you are observing for about 10 nights, 20 nights, and also signal is very faint. So that's why we developed another estimator. So this is one of the problem for the 21 centimeter cosmology. Wide field foreground, basically if your signal, so I said the primary beam, basically this is the primary beam pattern, and your signal is restricted, this tight signal is restricted. This is the phase center and only this part, 200 arc minute means 3 degree or something, 3 to 6 degree. But and this primary beam is very small at this point. But in your 21 centimeter signal is very faint. So even if a large bright point sources, suppose Phonex A or the center A, these are the highest bright sources, suppose 1000 Jansky. So these sources will contribute much as compared to the 21 centimeter signal, when even if they are outside, because we don't want that signal. Somehow we have to suppress the contribution. So that is wide field foreground. And also this figure which it shows, if any point sources are located at the outer region as a function of delta nu or frequency, it creates some oscillatory pattern. So this oscillatory pattern is very changing for every baseline. So you can't remove them with your efficient polynomial fitting or efficient algorithm. You can't remove efficiently. So that's why the outer sources are much contributing, basically affecting us for the 21 centimeter cosmology. Another problem is that uh, suppose a bright source is located, this is your phase center D, and any bright sources located at A, what will happen? This basically this is called the wedge plot. The 21 centimeter signal is reside only in the clean region, which is the blue region, and this lower right panel is dominated by the foreground that we want. But if any point sources located at far away, basically at the point A, this region, which is we know as a clean region, but this source will corrupt this region. So our aim is to remove this contribution or suppress contribution all over the outer region, and we are concentrated only in the center part. So that is one of the techniques or one of the algorithm we want to implement in our data, which will be beneficial for the 21 centimeter studies. And also it is efficiently, it should be efficiently fast, so that you can measure lots of many nights with less computational resources, and also the noise bias. So what we are doing here, this is the two-dimensional primary beam that I showed, is 1D basically Gaussian, but it is a 2D Gaussian. And these are the null positions. Okay. Now, we don't want this outer region, because if any strong source is located here, it will affect our measurement that I showed here. It will corrupt this region. Also, it will create oscillatory pattern, which all are difficult for 21 centimeter studies. So that's why we want to suppress the outer region. So we are multiplying this primary beam. Basically, you can't multiplying the primary beam with a Gaussian function, so that it is we don't, it is suppress the contribution from the outer region, and what you will get, this is the effective primary beam. But you can't multiply the Gaussian function in the sky, because so you can't do in the sky plane, you can't just multiply this Gaussian in the window. So what we are doing here, we are doing the convolution in the Fourier domain. Why were there two advantages? Because no need to go to the Fourier plane, because all the measurements we are doing in a Fourier plane. And if we want to multiply with some window function, what you have to do, you have to do a convolution. So that's we are doing here. We are doing a convolution in the Fourier plane, that is called that W function here. It is the Fourier transform of the window function, basically the Gaussian function. And when we convolve these visibilities, all the visibilities that I showed, the track, when we convolve these visibilities with this window function, basically you are multiplying your sky with this window Gaussian function, and you are less affected by the strong sources which are outside the primary beam. So that is the tapering, that is called the tapering. We are tapering the sky response from the outer region. And also we are not doing the convolution at each UV point, but in a grid, in a uniform grid, so that your computation is much less as compared to the earlier case. So that is the tapering and convolution we are doing. And we have developed estimator that is called tapered gridded estimator. And this term, again, the subtraction is the self correlation, that is to avoid the noise bias. So that we are doing convolution, subtraction, and finally with some normalization of the primary beam that we called as the MG, and we will get a angular power spectrum. So that is some normalization, okay, and that is the result. So that I showed earlier here in this plot, same power law power spectrum from the simulations, but here what we have done, we have convolved the visibility to suppress the convolution, to suppress the contribution outer region. We did the gridding to less for computational effort, computational resources, because for the large data set, and also the noise bias is not there. So this is the result of the tapered gridded estimator, and you can do efficiently, you can measure power spectrum efficiently from your visibility data using that estimator. And this I call, there are three novel features. It is gridded to reduce the computation. It suppresses the side lobe of the outer region where the bright sources are there, and also remove the noise bias. So this is one of the simulation result for the tapered gridded estimator. And this each blue, each white point at the bright sources. And we show that basically if any small scale structure present in your data, which located at the outer region or any small scale, it will give a bias in your measurement. So the red line we want to measure, but this small L values or small, sorry, the high L values or the small scale, you will get an bias due to these strong bright sources of the outer region. So And we can see in the black line that when we use the taper graded estimator, this black line, basically we are tapering the function, you can avoid this bias which are due to the noise, due to the point sources or any small scale structure. Also, you can remove the noise bias. Again, the noise bias is give a bias in your measurement in comparison with the red line that we measure. And you can see that when you apply the noise bias, you can measure with accurately. The bias is not there. So this is the advantage of the tapered graded estimator. We have improved from the bare estimator that I showed from the demo I have showed, but tapered graded estimator has some more advantages as compared to the bare estimator. This is also available on the GitHub. You can check that, but I will not show the demo here due to the time. And now I can show some of the application that we have done. What we have done, we have applied the TGE, the tapered graded estimator, to the all sky TGSS survey data. And this is the one of the largest survey at low frequency using the GMRT telescope that you have heard about, giant meter wave radio telescope. And we took all the data all over the sky, largest all sky survey, and we applied the tapered graded estimator to measure the angular power spectrum. Again, this is the two-dimensional power spectrum, and this has the third uh, mm, this is the total 2000 hours survey time, and this is 140 is the central 150 megahertz bandwidth. Sorry, 150 megahertz is the central channel, and 16 megahertz is the bandwidth. And number of fields, number of pointings is 5336. I showed the picture of one pointing here. This is one pointing, and it has observed many pointing, 5000 pointing all over the sky. This is the whole sky survey, and this is the result. We have applied the tapered graded estimator to all the fields all over the sky, and you can measure the power spectrum. And here you can see the upper panel are the equatorial coordinate, the lower panel is the galactic coordinate, and the left hand side is that we have not removed the bright sources. We not remove the point sources, because point sources are the one of the major foreground, and we have to remove them. Just the comparison we have shown left hand side, that this after removing the point sources, the amplitude is much less. This is only due to the galactic synchrotron emission, and you can see that uh, the galactic emission is much larger. Synchrotron emission is much larger at the galactic plane, but it is faint at the off galactic plane. So that we have measured using the TGSS survey and applying the tapered graded estimator. This is an efficient estimator. So I uh, so it is very quite efficient, also computationally much faster as compared to the earlier. So this is the all I wanted to say. And yeah, please, if you have a question, please ask.
Thanks, Sunita. Thanks for your presentation. So yeah, is there any question, comments? Please shoot. So while people are gathering their thoughts, so let me ask you something. So the last plot that you showed,
Yes.
It's what are you plotting there? Just the brightness temperature.
Yes, brightness temperature. Okay, let me go to the slide again.
No, it is the value of CL at a given L, right?
No, then we converted it as a brightness temperature. You can do that now. L into L plus 1 by, just let me go to the screen again. Yes, so this is temperature unit. You can convert the angular power spectrum as a temperature unit fluctuation. So root over of L into L plus 1 CL by 2 pi. So that quantity will give you the temperature fluctuations.
At that scale, at that L.
At that scale, yeah.
Right. So do you see that galactic, do you see any change in the galactic plane when you move to the larger scale? Yes.
Yeah, it is present at all scale. Yeah, because the intensity fluctuation is much larger at the galactic plane. So any scale it is visible. So this I am plotting where here only one scale, one L, but it is visible at other scales also, other multiples.
Okay. Okay. So I don't see any questions or raised hands here. So let me thank Samir Choudhuri for his kind presentation. And now I think we are at the end of the school, and we will, I think Samir Choudhuri will say the concluding remarks.
Yeah.